Structuring and analyzing big data. Structuring big data involves organizing and preparing the massive volumes of diverse data for analysis and decision-making. Several elements are crucial for structuring big data effectively. Data sources. Big data originates from various sources, including social media, IoT devices, sensors, transactional systems, websites, and more. Identifying and integrating relevant data sources is the first step in structuring big data. Data ingestion. Once data sources are identified, data must be ingested into the data processing system. This involves collecting data from disparate sources and converting it into a format suitable for analysis. Techniques such as data pipelines and extract, transform, load, ETL, processes are commonly used for data ingestion. Data storage. Big data storage solutions must be capable of handling large volumes of data efficiently. Traditional relational databases may not be suitable due to scalability limitations. Instead, organizations often use distributed storage systems like Hadoop Distributed File System, HDFS, cloud-based storage services, or NoSQL databases like Apache Cassandra or MongoDB. Data modeling. Data modeling involves designing the structure and relationships of data entities within the big data ecosystem. This includes defining data schemas, entity relationship diagrams, and data dictionaries. Data modeling ensures consistency and integrity in the stored data and facilitates efficient querying and analysis. Data processing. Big data processing involves performing computations, transformations, and analyses on the structured, semi-structured, and unstructured data. Distributed computing frameworks like Apache Spark, Apache Flink, and Hadoop MapReduce are commonly used for parallel processing of big data across multiple nodes. Data analysis. Analyzing big data requires advanced analytics techniques to derive meaningful insights and patterns. This includes descriptive analytics to summarize data, diagnostic analytics to identify trends and anomalies, predictive analytics to forecast future outcomes, and prescriptive analytics to recommend actions based on data insights. Data visualization. Communicating insights from big data analysis effectively often involves data visualization. Data visualization techniques like charts, graphs, dashboards, and heat maps help stakeholders understand complex patterns and trends within the data. Data governance. Data governance policies and practices ensure the security, privacy, quality, and compliance of big data throughout its lifecycle. This includes establishing data access controls, data lineage tracking, data quality monitoring, and compliance with regulatory requirements, such as GDPR or HIPAA. By addressing these elements effectively, organizations can structure big data in a way that enables efficient analysis, decision-making, and value creation from their data assets. Big data analytics refers to the process of examining large and diverse datasets to uncover patterns, trends, correlations, and insights that can inform decision-making, optimize processes, and drive business value. It involves employing advanced analytics techniques and technologies to extract meaning from vast amounts of structured, semi-structured, and unstructured data. Here's an overview of key aspects of big data analytics. Data collection and ingestion. Big data analytics starts with collecting and ingesting data from various sources, including databases, sensors, IoT devices, social media platforms, websites, and more. Techniques such as extract, transform, load, ETL, data streaming, and real-time data ingestion are used to gather data from disparate sources and prepare it for analysis. Data storage and management. Once collected, data needs to be stored in a way that facilitates efficient analysis. Traditional relational databases may not be suitable for big data due to scalability limitations. Big data storage solutions include distributed file systems, for example Hadoop Distributed File System, HDFS, NoSQL databases, for example MongoDB, Cassandra, and cloud-based storage services, for example Amazon S3, Google Cloud Storage. Data processing and analysis. Big data processing involves applying various analytics techniques to extract insights from the data. This includes descriptive, diagnostic, predictive, and prescriptive analytics. Descriptive analytics summarizes historical data to understand past trends and patterns. Diagnostic analytics identifies the root causes of past events or anomalies. Predictive analytics uses statistical models and machine learning algorithms to forecast future outcomes. Prescriptive analytics recommends actions based on predictive insights to optimize decision-making. Technologies such as Apache Spark, Apache Hadoop, and specialized analytics platforms enable distributed processing of big data across clusters of servers. Data visualization and reporting. Data visualization plays a crucial role in big data analytics by presenting complex information in a visually appealing and understandable format. Tools like Tableau, Power BI, and Matplotlib enable users to create charts, graphs, dashboards, and interactive visualizations to explore and communicate insights derived from big data analysis. Machine learning and AI. Machine learning, ML, and artificial intelligence, AI, techniques are increasingly used in big data analytics to automate processes, discover patterns, and make predictions. ML algorithms like classification, regression, clustering, and neural networks are applied to analyze large datasets and uncover hidden patterns and relationships. Scalability and performance. Scalability and performance are critical considerations in big data analytics, given the large volumes and high velocity of data. Distributed computing frameworks, parallel processing techniques, and cloud-based infrastructure are employed to handle the scalability and performance requirements of big data analytics applications. Data governance and security. Data governance policies and security measures are essential for ensuring the privacy, security, and compliance of big data analytics initiatives. This involves establishing data access controls, encryption, data masking, compliance with regulations, e.g., GDPR, HIPAA, and monitoring data usage to prevent unauthorized access or misuse. Overall, big data analytics empowers organizations to derive actionable insights, improve decision-making, enhance operational efficiency, and gain a competitive edge in today's data-driven world. Elements of big data. The elements of big data, often referred to as the 3 V's, volume, velocity, variety, along with additional characteristics, are crucial for understanding the complexity and challenges associated with big data. Volume refers to the vast amount of data generated and collected from various sources. Traditional data processing systems may struggle to store and analyze such large volumes of data. Examples include petabytes or exabytes of data generated by social media, IoT devices, sensors, and other sources. Example: an e-commerce website collects terabytes of customer transaction data daily, including purchase history, browsing behavior, and clickstream data. Example: social media data. Social media platforms like Facebook, Twitter, and Instagram generate enormous volumes of data every day, including posts, comments, likes, shares, and multimedia content. For instance, Facebook processes billions of user interactions daily, leading to petabytes of data storage. Velocity describes the speed at which data is generated, collected, and processed. Big data often arrives in real time or near real time, requiring rapid processing and analysis. Examples include streaming data from social media updates, sensor data from IoT devices, and financial transactions. Example: a telecommunications company processes millions of call records per second to detect network anomalies and optimize network performance in real time. Example: sensor data from IoT devices. IoT devices such as smart thermostats, wearable fitness trackers, and industrial sensors generate data in real time. For instance, sensors in a manufacturing plant continuously monitor equipment performance, producing a stream of data about temperature, pressure, and other variables, which must be processed rapidly to detect anomalies or prevent failures. Variety refers to the diverse types and formats of data, including structured, semi-structured, and unstructured data. Structured data, organized and stored in a predefined format, for example, relational databases. Semi-structured data contains some structure but does not conform to a rigid schema, for example, JSON, XML. Unstructured data lacks a predefined structure and includes text, images, videos, social media posts, etc. Example: a healthcare organization collects structured data from electronic health records, EHR, semi-structured data from medical imaging systems, and unstructured data from patient notes and social media for disease surveillance. Example: healthcare data. Healthcare data comes in various formats, including structured data from electronic health records, EHRs, unstructured data from clinical notes, medical images like X-rays and MRIs, and semi-structured data from wearable health monitors. Integrating and analyzing this diverse data helps healthcare providers improve patient care, identify trends, and develop personalized treatment plans. Variability describes the inconsistency or fluctuation in data formats, quality, and meaning. Data may vary over time or across different sources, making it challenging to integrate and analyze effectively. Examples include fluctuations in customer behavior, market trends, or sensor data readings. Example: financial market data. Financial markets experience fluctuations in data over time, including stock prices, trading volumes, exchange rates, and economic indicators. For example, stock market data exhibits variability due to market volatility, news events, and investor sentiment. Analyzing this data helps traders and investors make informed decisions about buying, selling, or holding assets. Example: an online retailer experiences fluctuations in website traffic and customer behavior during holiday seasons, leading to variable data patterns that require adaptive analytics and resource allocation. Veracity refers to the reliability, accuracy, and trustworthiness of the data. Big data may include noise, errors, biases, or inconsistencies, affecting its quality and reliability. Ensuring data veracity is crucial for making informed decisions and deriving meaningful insights. Example: a financial institution analyzes market data from various sources to make investment decisions. Ensuring the accuracy and reliability of financial data is crucial to avoid erroneous decisions that could lead to substantial losses. Example: customer reviews and sentiment analysis. Customer reviews on e-commerce platforms or social media may contain inaccuracies, biases, or spam. Conducting sentiment analysis on such data involves assessing the veracity of opinions expressed by users. For instance, a product review may be misleading if it's posted by a competitor or influenced by incentives. Analyzing sentiment helps businesses understand customer preferences and improve products or services. Value represents the ultimate goal of big data analysis, extracting actionable insights and creating value for organizations. Value can be derived through various means, including improved decision-making, enhanced customer experiences, new revenue opportunities, and operational efficiencies. Effective data management, analysis, and interpretation are essential for realizing the value of big data. Example: a manufacturing company analyzes sensor data from its production lines to predict equipment failures and schedule proactive maintenance, reducing downtime and optimizing production efficiency, resulting in cost savings and improved operational performance. Example: personalized recommendations. Online retailers like Amazon and streaming services like Netflix analyze large volumes of customer data to provide personalized recommendations. By analyzing browsing history, purchase behavior, and demographic information, These platforms suggest products or content tailored to individual preferences. This enhances user experience, increases customer satisfaction, and drives sales. Understanding and effectively managing these elements are key challenges in the era of big data. Organizations must employ advanced technologies, analytics techniques, and data management strategies to harness the potential of big data and turn it into valuable insights and opportunities. Do like, share, and subscribe and comment. Thanks for watching from Edspirational-techies.